So hello everyone, I'm Rawana Sarsawi, a research member at the AMRL lab, the Additive Manufacturing Research Lab at University of Regina. And today in this tutorial, thank you for checking the tutorial by the way. And in this tutorial, we're gonna talk about the lightweighting technologies and the lightweighting techniques in NTOP, specifically the topology optimization. And why am I saying topology optimization? To be precise, is that lightweighting has so many different techniques, split into basic and advanced techniques. And using these techniques, you can achieve the lightweighting that you want. So what is lightweighting in general? Lightweighting is a process when you have like a body or like an assembly or a single body that you wanna reduce the mass or reduce the volume of material used in there, and without touching or without affecting the mechanical properties that you wanna have with the body. With the techniques that are provided for lightweighting in NTOP, you can have the basic ones such as the shell and infill. For example, when you want to have like a proper thickness and at the same time to reduce the material inside, and in this case you want to have like a good impact resistance. And another one is the lattice structure, when you change your body features into lattice, which reduces the volume and reduces the material. Another one is the conformal ribbing, when you have a thin wall, but in the same time you want to have some ribbing support structure inside, just to support the thin walls. Another one is the topology optimization, which is the one that's going to be discussed in this tutorial. And there is another technology in the basic technologies, which is combining the technologies. So for example, if you have like a body that you want to improve its weight or reduce its weight and reduce the mass and the material used in there, and at the same time you want to have a good stiffness and an impact resistance, which cannot be achieved by topology optimization. So you may take your body and let it go through a topology optimization, and after that you can let it go through another step or another technology, such as, for example, the shell and infill, to improve its impact resistance. And of course, there are other techniques, which are the advanced ones, such as the assembly consolidation and the multifunctional lightweighting. It all depends on your body, and the advanced technologies are mainly for the assembly, if you have like an assembly instead of a single body. So right now, as you can see, that's the main screen once you start your NTOP. And here you can see that there are different case studies, depending on each like target that you want to have. Like, for example, the heat exchanger, the topology optimization, each of them is a specific case study where you have the BART, you have the steps, and it's a good idea to start with them to just check an overview before going into the program if you're a beginner. And to start right now, we will start with a new file. And the first step I would recommend in this case, and especially for the topology optimization, is you will have a lot of meshing and a high number of elements produced in each step. So that may be hard for your processor. So it's a good idea to save first before you do anything. Let's save it. Okay. So here you have your interface, your user interface, and here are the sections and the input sections where you will start putting your blocks and your commands. So it's a good idea to divide your work flow or your work notebook into different sections and to give names for each section. For topology optimization, you have two options: either to start the design itself into NTOP and to create your design and everything inside NTOP, or to import it from an external source as a CAD body. So for me, I'll import it as a CAD body. And actually, the sequence of this session will be that we will import the design, the CAD design, and then we will do the FE meshing, FE modeling, topology optimization, and then we will have a static analysis for both bodies to compare the effect of the topology optimization on the maximum stress and strain. So the first section here will be for the geometry, where we will import our geometry. So our geometry is a CAD body. So you'll have the block as import part, just the part, and select it from the files that you have here. I already have it as a bracket design. and you can see it here. So for this bracket design, we will have a part like a mass coming here, giving a load, and we'll have other loads coming as the four legs here, and then we will have the hinge or the hanging structure coming here. So we'll have a displacement constraint at this area. So that's our part. It's important to start dealing with the part. You'll have to transfer it into a CAD body variable. So in order to be able to get the structure of the body and to get an overview of what parts are there, what bodies are there, what boundaries are there, what components are there, you have to transfer it into a variable. And make sure to give a specific and a proper name for each step that you have. So that's a CAD body. Let's call it our original body. And that's for the original body. Now for the next step is to specify each face that you wanna have it fixed. Like for example, when I'm going and undergoing a topology optimization, I don't want this area to be touched. I don't want this material around this area to be removed. So that's why I need to specify it as an interface. So you'll have two different steps. The first step is to identify all the interfaces as a one body list, CAD face list. And the other one is to specify each face by itself, which will help us later on in the boundary condition selection. So let's start with identifying the faces that we want. So I want this one. I want, of course, the four legs to not be touched, and these will be our interfaces. And of course, when I hang the body or when I hang the bracket, this face will be touched as well as this part, which will be like in direct contact with the hanging structure or the linking bar. And to transfer it into a face list, a CAD face list, you have to right click on your mouse and then create CAD face list variable. So variables is a good thing. It's a good thing to have each block as a variable, because having each block as a variable will allow you to use that variable later on, will allow you to use that block without leaving it, without making it disappear from your notebook. So for example, if this is not a variable, once I try to use it into another block, it will be a one-time input. But if it's a variable, it will be more than one-time input, so I can use it in several blocks, more than one block as an input. And it's already created as a variable. Now we'll make this one our interfaces. These are the interfaces that will be used later on in our topology optimization. Now for our boundary conditions, we know that we will have a boundary condition in here. We know that we will have a force at this area. And we'll rename this variable as the main body, the main part. And then we will have four forces with the same value at these four legs. So these can be named as the guides, the L guides. And then we'll have our restraint, which is the hanging structure, will be at this face and this part here. Okay, so that's the first part, which is the geometry. And for right now, we don't need to add anything else. But maybe during the steps or during the further process, we can add some other parts in the geometry section if it's needed. So the next step is to create your FE mesh and FE model. So for topology optimization, your topology optimization block won't accept any non-finite element block. So you have to have your FE model, the finite element model, and the FE mesh. In this case, we'll call this one the FE model for the original part, for the original body. The first thing you need is the FE mesh, of course. So here you have two approaches to work this process. The first approach is the top bottom, which you go from the mother block, which is the FE mesh itself, and then go step by step to see what kind of input is needed in each block. And the other one is to start from bottom to top, which you start with the simplest part and then keep adding blocks after each other. But for the bottom top approach, you have to to be really like experienced, and you have to have good knowledge of the blocks needed as a next step. So for me, I would recommend if we go as the top bottom, when we start with the mother block, you want an FE mesh, an FE volume mesh for the whole volume here. So for any block, you need to specify the domain, and that domain has its input. So that's our domain here. And that gives you as the input for this domain is the volume mesh. So you have to have a volume mesh, and we don't have a volume mesh in this case. So we'll have to create our own volume mesh block and insert it as an input. You have two ways, either to insert it outside as a volume mesh, like that, and then insert it in there. And as you can see here, because I didn't change it into a variable, so once I put it, it was a single time input. So I cannot really put it into another block as an input. Or you can just write directly here, volume mesh, and voila, it's your input. And then for the second domain, for the domain of the volume mesh, what's required here is a mesh. So as a step, you have two options. For the volume mesh, it's either to put the mesh directly, but then you will have some trouble because that's a volume mesh. It will give you the volume directly without meshing the surface, the external surface. So it's a good idea to have, before the mesh, a remesh surface block. So in this case, after you have your mesh block, the mesh block inside the volume mesh will go through a remesh surface. So you'll make sure that you have the mesh for internal structure and for the surface, and then all in all, we'll go through the volume mesh to make sure that the whole volume is meshed already. Now for the input in here, it's the mesh finally. So you have several options to get your mesh. So you have the mesh from CAD body, you have the mesh from implicit body, from voxel grid. So that depends on your input for the mesh. So what part would you create the mesh for? It's this one. It's your original body, which is a CAD body. So in this case, you'll select the mesh from CAD body, and you'll make your input the original body here. Now we'll start inserting the other inputs that are needed for the mesh structure. After specifying the domain, we'll have to go through the inputs. The tolerance as it is, you can change it if you want to improve your quality later on, or if you're having trouble with your mesh being generated. But as it is right now, it's fine. Now for the edge length, as the edge length will be an input for several parts later on, so it's a good idea to create it, to make it a variable outside. So in this case, you'll specify the edge length only once, and if you have any changes in your design later on, you can just change the edge length in here in this block, and it will automatically be changed in all the other blocks where this edge length is an input there. And for this situation, I'll write, for example, 2 as an edge length. See what happens. So there would be a problem in this case, that I didn't specify a unit for the edge length. So the edge length should have a unit which is millimeter. If I keep it as it is right now, it will create an error once I identify the rest of the inputs. Like I have it here, I'll create the geometric order as a linear. You have the quadratic and linear orders. So it's a good idea to have it linear. So the difference in the geometric order is it's the way how the nodes from the neighboring parts are connected together. So the linear is the best way to have like a simplified mesh. And then the shape here is a triangular. It doesn't matter, but the triangular is the best one to have like small units of mesh. Now you can see there is an error for generating. And once you check it here, the edge length requires units of length. So that's because we didn't specify a unit of length for the edge length. And that happens at the first time you input the value of the edge length, so you have to specify your unit. See, once you specify the unit, it's given outside as millimeters here. Now our part for the FE mesh is done. To check how it looks like right now you can see that it's not really obvious because you have several blocks visible at the same time. So it's a good idea to specify your only, and to make only the FE mesh visible. You can just select your block and then press I from the keyboard. That will only make this block visible. As you can see, these are the meshed parts. So some notes for the volume mesh. So this part is simple. So it doesn't really have problems when creating a volume mesh. However, you may have some like some hard parts, or for example, this part is already designed in Fusion 360 as a single body directly. So it was the block, and then the material were subtracted from there. However, for some designs, you may have some kind of an assembly where you have other parts and you're linking them and combining them into a single body. So the final result is a single body. However, the software doesn't really approve it as a single body because it already understands that there are some parts combined together. So that's why you may have some reinforcement problems with the mesh, or maybe like the intersecting sections in the mesh. So it would be a good idea if you're having trouble with your intersection parts in meshing, to have an extra step here instead of having the volume mesh, but to have the robust tetrahedral mesh. So it's a robust tetrahedral mesh instead of the volume mesh, to make sure that all the joining parts will get their mesh properly. However, it's not needed in this case, so we won't really use that block. And now we have our FE volume mesh. We'll change it into a variable again, FE mesh for original. And why am I specifying for original or top opt? Because after we have our top opt, we will have to go through a static analysis where we will need to do an FE mesh and FE model for also the topology optimized design. Now, as a next step to transfer our FE mesh into an FE model, FE solid model here. As an input, you'll see that you need your FE mesh, which is already there. So one way is to drag it and put it, or just like to press on this arrow and then stop on it, click on it. It will be inserted directly as a solid mesh. So to have an FE solid mesh, it's similar to have an FE mesh. Sorry, an FE solid model. But in this case, in case of the FE model, you'll have to specify some other inputs. So they're almost the same. They give the same result. But for the FE model, you'll have to specify some steps to make sure that your part is solid. So in case your model is not really solid and you'll have some liquid flows or some like elastic parts, you won't really use the FE solid model, but you'll use the FE model and then start specifying your components. For our part, in our case here, it's a solid model, so we'll go with the FE solid model. And then we'll have to specify the material. So one thing to know about the topology optimization in NTOP, it allows only the isotropic materials. So right now, it may have some errors and trouble to process other types of materials. So it's a good idea to go with the material to be isotropic. So we have an option of selecting the isotropic material, but in this case, you'll have to insert the properties of your material depending on the material that you're using, or to just use an already existing material that you know it's isotropic. For example, aluminum here, it's isotropic material, it's written here. And you don't need to specify anything else. So that's your FE solid model. I'll make it a variable. Oh. And it's seen here. That's your FE model. Now let's rename it FE model. Okay, that's the FE model and FE mesh part. Now the next step before doing our topology optimization. So for a topology optimization, you need the FE model and FE mesh. You need boundary conditions, and then you'll specify some other parameters inside the topology optimization block itself. So before we go to the step of topology optimization block, you'll have to specify our boundary conditions. So you'll make a section for the boundary conditions for original. Now at this one, you have two ways of specifying your boundary conditions. So for example, let's say that we want to add a force, okay? That's the force. So you need to specify your boundary, the FE boundary. So the FE boundary in this case is the interface where you want to have your boundary condition, or you want to have your force there. So you have several ways of getting the FE boundary. So you have the FE boundary by body, FE boundary by flood fill, and FE face boundary. So in case you have your body already imported as a CAD design from an external software, it would be a good idea and the easiest idea to proceed with an FE face boundary, which directly selects the face with a good accuracy. However, if your design was already designed in NTOP but not imported from an external software, then in this case you cannot use the FE face boundary, but you rather would use the FE boundary by flood fill. Unlike the FE boundary by flood fill, the FE boundary by body is only dedicated for the implicit bodies. So for our case, we can use the FE boundary by flood fill or the FE face boundary. And let's try each of them for each force, because we will have two different forces, a force here and the force at the forelegs, and we will have the displacement restraint here. So let's start here by an FE boundary by flood fill. So here the first thing it asks for is the mesh, right? So you'll select our mesh and then the entity. What is the main parts that you want to keep and preserve during creating this FE boundary? Like the force would be along the whole edge or along the face or along the nodes of the body. So in our case, we'll take it as nodes because we want it to go through the whole plan. And then the origin. Now that's the difference between the FE boundary by flood fill and the FE boundary, the FE face boundary. So by flood fill, you have to specify the origin, and once you specify the origin and the direction, it just selects the closest and the nearest meshed surface, and just flood fills the area as if it's the boundary. So you can move your arrow as close as possible to the area. We want it to be this part. So that's the closest. And as you can see here, it selected the whole face. That's by flood fill. So this one will be inserted here, and that would be force number 1. So if you rename it while it's a variable or rename it as an output, the name will be the same. So if you rename it while it's not a variable, once you transfer it into a variable, the name will be taken for the variable as well. So this one will be force 1. And here for your vector, the vector here specifies the value of your force. So our force, let's consider that our force is a unidirection, so it's having an effect only at z. So that's why we'll keep the x and y 0. But our force will be the gravitational effect, has the gravitational effect and the weight effect of the material put in here. So we'll consider, for example, as 5 newtons, and I made it negative because my force is pointing downward. And as you can see here, the glyphs, the yellow glyphs, refers to the force. So that's for the force number 1. And we'll make it a variable. See, it took the name directly that we specified before. Now for the next part, for the next force, we'll specify the boundary, but in this case, it will be the FE face boundary. Yeah. So for the FE face boundary, you just have to insert the CAD face list that you specified. So for example, I want this force to be applied at this section here, the section here, the other sections. So in this case, we will make use of the previously defined faces at the geometry section. So it takes the CAD bodies or CAD face lists. We'll take the LG guide. So you cannot import or put a list into a list as an input. So that's what happened earlier. As you can see here, it's already inserted as a CAD face list. If I put this one as a list in there, it won't be accepted because you have a list and you're importing a list into another list. So that's not really acceptable. In this case, you'll have to remove the initial list and put your original list. But if you want to have your list combined, then there are some features or some functions added by NTOP to add them together, such as the stitch adjacent CAD faces. If you're having the list into your list, your original list is a CAD list, and you want to add it to another list, then you can use the function stitch adjacent CAD faces. But that will only be helpful and functional if your part is adjacent, if your faces are adjacent to each other. And now for the mesh, it's asking for the mesh. We have it here, and the entity again, nodes. And see, that's the force here. If I show only this part, that will be the boundary condition. And of course, we need to give a value for the force. Like, see, here there is no force because we didn't give a value for it. That's why there is nothing showing. So you give a value, or 0, and in the Z direction, we'll make it a 2. And directly it showed you the glyphs, the yellow glyphs for the force along the light guides, or the guiding lines. Yeah. And we'll make this one a variable, force 2. Then for the last boundary condition, which is supposed to be the one here at the hanging structure, and that would be a displacement restraint. In this case, we will use the FE face, the FE face boundary. And again, we will delete the face list and put our hanging structure face list, the mesh as needed, and the entities as required. I'll transfer it into a variable. Okay. And in this case, it's a red glyphs for the restraints, for the displacement restraints in general. And here we have our boundary conditions. Now we're ready to go to the next step and to start creating the topology optimization. For a new section, to create a topology optimization, we have to have a topology optimization block and start to check the requirements for each step. So it's again the top-bottom approach. You're using the mother block to continue. Okay, that's the topology optimization. So the first thing for the inputs is the model, the FE model, which is here. And now for the objectives. So to define the topology optimization, you have to give objectives and constraints. And the objectives here refer to the target, the main goal that you want to achieve by your topology optimization. So for the objectives, you want to optimize the objectives, and you want the optimization of the objectives. But what are the objectives? The objectives in this case are referred to as responses. So the response or the result that you want to get from the topology optimization. You have several types. So by double-clicking on the main input, you can see what kind of inputs that you can have. So in this case, you have several responses, such as the center of mass response, displacement response, mass, moment of inertia, natural frequency, stress response, structural, and volume fraction responses. These can be achieved also from the light weighting label here. And for our part, so each of them refers to something. So for example, the volume fraction response is to make sure that your final target is a specific volume percentage, and that volume percentage will be kept at this area, for example, or it will be distributed along the whole body, or your final design will be lightweighted by this percentage. Another one is the structural compliance response. So the structural compliance response, if you want to increase or maximize your structural compliance, in this case, you're decreasing the stiffness, which is something not favorable for our part. So you can have as many responses as you need, depending on your part and depending on the force inputs that you're having. So for our part, we'll go with the structural compliance, and we will also specify the volume fraction. But the volume fraction will be a side effect of the, not a side effect, but a limiting factor or a constraint for the structural compliance, because I want my body to have its volume reduced while not affecting its stiffness. I want it to be stiff and with a good mechanical feature and strength. So that's why I'll go with the structural compliance as the main response. And in this case, I have to identify the boundary conditions. So I will add the 3 boundary conditions specified earlier. Now you have here a feature called an input called region. So for this region, it states that you don't want to have this applied to the whole design, but rather specify an FE region, and you want that to be applied to only that region. And it's not the case for our design because we want to have it for the whole body. So the next thing is the weights. So the weights here is an input if you have several responses and you want to give weight for each response. So it's like the favorability of each response. I want this response to be focused on with 60%, for example, and another response 40%. So how the priority will be given for each response. And in this case, I only have one response, so I don't really need to specify any weights. And by the way, if you don't specify the weights and you have more than one response, then in this case, each response will be given an equal weight, an equal importance, which is not needed here. Now we're done with the objectives, responses. The next thing is the constraints. So the constraints are some kind of a limiting factor for the responses. So for example, I said that I want my structural compliance to be minimum, to be minimized. However, the constraints states that I want it to be minimized, but I want to keep that thing fixed. Or for example, if I give the constraint here as the volume fraction constraint, which we will give, then in this case, I want to say, or I want to tell the program that minimize the structural compliance without affecting the volume fraction. I want the volume fraction to be with this percent. I want the final volume to be with this percent from the original volume. And I don't want it to be affected by the structural compliance. So it's just like a limiting factor to tell the software when exactly to stop. That's our objective. And now that's here for the constraint. So before mentioning the volume, let's see what kind of constraints that we have here. So the constraints have in here, like the design response constraint, displacement constraint, extrusion, overhang, passive region, planar symmetry, and stress constraint, and volume fraction. So the volume fraction gives a specific volume percentage that you want to keep from the original design. So I want this percentage to not be touched. I want it to be kept. And then for the planar symmetry, for example, if you have a design where there is a symmetry along an axis, and you want to make sure that whatever is happening on this side will be repeated and as a symmetry on the other side. Passive region constraint, for some reason, sometimes topology optimization start to eliminate parts from the model, from the body, if the boundary condition were not specified enough. So for the passive region constraint, you have to give an FE region and then put it there, and that will tell the program that do whatever you want, do whatever steps and process you want to achieve the objectives. However, don't touch this region. That's a passive region, do not consider it a part of the model. So for our design, we'll go with the volume fraction constraint and the value here. So the value is a percentage that we ask the program we want to keep, or we want to have it remain there. So I want my topology optimized body, for example, to be 10% from the original body, or 20% from the original body, or whatever. So if I give it like 0.1, then in this case, I want it to be 10% from the volume of the original body. So I'll give it as a 10%. And now we're waiting for the topology optimization to be produced. So the final result won't really be a good looking form, because it's optimizing, removing the material, removing so many extra material, and it's not really integrated to the intersections of the original body. So that's why we will have to go through several steps for like post-processing. While we're waiting for the topology optimization to be final, or to see the results of the topology optimization, let's think about what kind of steps we need to smoothen or to work on this body to make it like an applicable body for additive manufacture and printing. So the result will be similar to this view or this shape, and that's not something that we need. So first of all, the surface is not smooth, it's really rough. So a first thing that I want to do is to smoothen that surface a little bit. So I'll have a smoothen block. That's for making the body smooth. Now we have the result of the topology optimization, as you can see here. And as I said, the surface is not smooth enough and it needs further processing. So in this case, we'll have to start working on the smoothening of the surface, and that's why I will add a block for smoothening. I cannot add it there because it will accept only implicit body. So I'll have to transfer this one into an implicit body. And first I'll make it a variable. That's the topology optimized one. And we'll have an option for implicit body from topology optimization. So we'll get the implicit body. And here, the number of iteration doesn't really matter, but it's up to you how much details you want to keep and preserve from your body. So it doesn't really matter. Just give it as a 2. And then I'll insert it here. So instead of putting it as a one-time variable, we may need it in further steps. So that's why we'll make it a variable as well. And we'll make it as top. Let's make it as 1. That's the first implicit body that we need here. So to make sure that your smoothing is in the best quality ever, you'll have to go through some steps here. So the first one is the grid size. The grid size affects the smoothing highly. So it's a recommended feature that you have your grid size double the minimum features, the minimum element size that you have, and then start to reduce it one by one. So for me, I would prefer if I go with the 1 as 1 millimeter and then start reducing. So if I make this one only like that, it's nothing really. So that's why that's not the best smoothing surface that we need. So that's why we will have to change some other things. Interpolation type, the best quality is preserved with the cubic interpolation type. And then for the grid size, it's high. So that's why we will reduce it again. So it's like how much material you're removing to smoothen your surface. So that's somehow acceptable for the surface that, like, as compared to the previously stated one. So it's almost the same, but more smoothened surface. And now we have the smooth body. We'll make it a variable, smooth body. Okay. Next step is we have the smooth body. So that smooth body will say that it's the topology optimized one. That's the final version of the topology optimized one. Now we want to modify it and integrate it to the original body in order to have a proper body to print. So the first thing is to do an intersection, to do a Boolean union, sorry. That Boolean union will unite your smoothened body with the interfaces. So we should have this Boolean body, this smooth body, with the interfaces that we already specified earlier, right? We had a part for the interfaces. It's not here right now, but let's specify again. Should be here. These are our interfaces. Let's take it here to make it easier. So these interfaces should be connected with the smooth body. to make sure that they are united, and that's the part that, or these are the areas that we don't want to touch or we don't want to affect. So the first thing we need to do is to make sure our interfaces themselves are connected together, because as you can see here, they are not connected at all. From this part, we need to do a union for the interfaces, which are these ones. And these interfaces are not really connected together, and they are in the form of a thin wall. So it won't really have any, it's treated not as a body, but as a surface. So in this case, we will have to have a thickening for these interfaces to thicken the body, and we want it for the interfaces. It's not accepted, of course, because we need an implicit body. So an implicit body from CAD body. And then we will put our interfaces. Now I want the thickening to be by 2 millimeters, for example. So the surface should be thickened now. And as a next step, we'll put them together as a part here with a different thickening amount. So the design is not really the best right now, but after we do some several processing, post-processing, it should get the best quality. That's a Boolean union for only this body. Yes, and that's the tolerance, and be 0.1, it's fine. And the thickness is 2, that's fine. Next step is to do a Boolean union. But between the interfaces and the smoothened body. So that's why we have two bodies here. You have the smoothened body. And we need to modify blend radius so we get the best result. So if you see it here, that's acceptable now, but it can be changed later on according to the process and according to the final body that you want to have. Now we already integrated the smoothened body from the topology optimization and the interfaces that we want to keep in our body. So in this case, we have the preserved areas that we don't want to affect, but we want to integrate it to the original body and then eliminate the extra material and the extra mass. So in this case, we will have a Boolean intersect that gives you only the intersections with a good quality between the preserved areas and the main body and the original body. And in this case, we will put the Boolean union, the whole thing together. And as a second body, you will have our original body. That's the result. And if you're having trouble with your results, that means you maybe didn't define the faces that you want in a proper way, but it's an acceptable version. So you have your areas that you want to preserve, and you have the qualities of them. So that's a Boolean intersect. And these are the parts that we want. We can increase this one again, just in case if you have a better result. And that should be the final result of our topology optimization. We can make it a variable and call it the final. That's the final version of topology optimization in this case. Now, to make sure whether the mass or the weight was conserved or not, and what is the difference between the weight of this topology optimized part and the original part, we have a block called the weight saving, which gives you a comparison between the two bodies and gives you a specific number and a specific value of how much mass is reduced in the second one. So it's different from the volume fraction constraint, because the volume fraction constraint tells you what percentage of mass we want to keep. So I don't want to keep more than that mass, or I don't want to keep more than that amount. But in here, it shows you how much percentage of mass was preserved. So you'll have the light-weighted body here as a final, and the original body here. And it's processing. So our final body is 25% less by volume from the original body. That's the part of topology optimization. Now, to check the strength of our final body and the topology optimized one, you'll have to go through a static analysis. So we have a block here for the static analysis. So this is a static analysis that can be done for the original part. Let's just delete it and start it all over again. Okay, so for the static analysis, we will need the FE model. And in this case, our FE model is here. That's for the original part. And then for the load conditions, we have them already here specified as load conditions. So it already gives you only one input if you have only one load condition, but a static analysis or any kind of a simulation will not be run with less than 2 boundary conditions. So at least you have to have 2 boundary conditions. And in our case, we have 3 boundary conditions. And that's the result of the static analysis for the original body. So the main concern that we have is the stress, and that's why we will check the maximum and minimum stress for this case. And we have here a maximum stress of 1.006. So this value, we need to keep it in mind because our final topology optimized part has to have a static analysis and a maximum stress that is not way higher than this amount. So it should be as close as possible to this amount. So it's a hard estimation to say that it will have a maximum stress less than this number because it's with less material. So more stress will be applied to the structure. However, we are our target here is to minimize the maximum stress as much as possible. So to get the static analysis from the topology optimized one, you'll have to go through the same steps and get an FE model and then a static analysis from the topology optimization. So to get an FE model, we will have to have our topology optimized part not as an implicit body. And it's here already as the final version. It's the implicit body. And again, the same steps, the mesh from implicit body, remesh, volume, and FE volume mesh. We'll just import it as an input. And that's for the mesh. It will have some hard time to process, to give you the results. And then, of course, for the FE model, for topology optimization, it will be also the same steps. And we will insert the FE mesh. Both of them combining right now. Now, while these ones are combining and processing, you'll have to have another version of our final body. So to select the boundary conditions in this case, it will be hard to select it with the final final topology optimized one. So in this case, we will have to transfer it into a CAD body. So we will be able to select the faces and the surfaces in there because it's right now treated as a single block. So no faces, no face variables in there. So we will have here, after we are done here with preparing the FE mesh from the topology optimization, and we already created the FE model topology optimization from the FE mesh. So they'll take some time to run. And while they are running and preparing the meshed file, we have to start preparing another step, which is, we'll have to start preparing another step, which is transferring the body into a CAD body. Because in this case, the software is treating the body as a bulk body. It doesn't have any specific spaces or any specific like edges or anything. It's just like a single body, single solid body. So we won't be able to make it run a static analysis without specifying the boundary conditions. So to make it like understand the faces and specify the faces, we will have to transfer it into a CAD body. So for that purpose, you'll have to add a block here, which is CAD body from Quad Mesh. And as you can see here, the domain that it asks for, or the input it asks for, is a meshed body. So we will start transferring this body into a mesh body. First thing, we have to go through a quadrant mesh. And this quadrant mesh will ask also for another mesh. So we're going from the mother cell, from the mother block, into step by step till we reach the mesh from implicit body block. So for the quadrangular mesh here, we will have to have a refined mesh. It's just the same steps that we already generated previously, but previously we used the remesh, and right now we're doing the refined mesh because our body is already a single body. And now we will want a volume mesh, and then mesh from implicit body, where we can insert our final topology optimized body. And it won't run without inserting the rest of the inputs, which are like the tolerance. We're using the same tolerance everywhere here. Of course, you can change the tolerance if your part is complicated or you're having trouble with your mesh being generated. And the edge length, we can use our edge length previously specified, or we can just like specify another edge length here. It would be a good idea if we would just take one of the edge lengths that we specified as a variable outside the block. So in case we want to change it, we can just like go and change it directly into the variable. And yeah, the refining steps, we'll take it as 2, and it will start generating the mesh. So we have 2 steps here. Once we have our FE mesh ready and the FE model ready and also the CAD body, once the CAD body is ready, we can just like make it visible and start selecting our boundary conditions. So you'll have the boundary conditions. Again, the same force will be applied here, 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 and there, and displacement restraint at this area, which we preserved already. That will be needed for the static analysis here. And we will do the same things that as we did in the original body. So as it will take some time to process, I have already a prepared file. And let me show you first here the original, and that's the original design. That was the original design. And that's the final design. You'll see that it's a little bit different from the previous one that we are having here, but the result will be the same. So the difference is the faces, the interfaces that I selected in both files. So for this one, I selected the main slit, the whole walls of the slit. On the other one, I selected only one wall with the bottom part. So it doesn't matter; it will give still the same values or similar values. In this case here, you can see that we have already the CAD body, the final CAD body, which will be in this shape and this form. And these sections, that's just due to transferring the meshed file into a CAD body. So that's why it's not really treated as a single face into one part. They are rather transferred into segments. So these segments are used later on in specifying the face. So I'll have these ones to refer to the first force. Create a CAD surface. That's force 1. And then I'll go to these parts. I'll repeat the process again here and here. And in the end, I'll have these 3 forces, or these 3 parts. Not the forces, but the boundary conditions. These 3 boundary conditions. And they are here as a CAD faces, like CAD face list. So inside the static analysis, you'll have to insert, again, the model, the FE model, as requested, the load conditions. You'll have. So what I did here is I already created the blocks inside the blocks, unlike what we did in the original design, where here you can see that we created already the boundary conditions and the forces and the restraints outside as a separate block, and then we started importing them into the input. However, in here, I created them directly inside the static analysis block. The force, I give the same values, -5 and -2. And let's run the static analysis and see. So that's the result of the static analysis. And of course, as I said, the main concern is the stress. So as a maximum stress, it's 1.26. So remember the maximum stress that we had in the original design? Static analysis done in the original design. Should be here. Yes. And in here, the maximum stress was 1.006. Here, it's 1.2625. So that's not the same, or that's not less, which is understandable because we have less material in here. So the stress will be a little bit, or a little bit higher. And as the maximum stress for the topology optimized design gets closer to the maximum stress in the original design, that gives us an understanding that our topology optimized design is better and like more reliable, because we're having this maximum stress with a weight saving of 22.7%. The volume was reduced by 22.7%. That would be the final result from the other file. And yes, that's the end of our tutorial. Thank you so much for listening.